Scientists may have found a hole in the universe, 2 billion light-years across. But is it really a hole, or just a cosmic illusion? You are drifting across a valley in space 2 billion light-years wide. Could it chill the ancient afterglow? Could it tug on passing light? What appears to be black quiet is not the absence of everything. It is a stretch where galaxies thin out and the bright threads of the web loosen. The shape is irregular, like a coastline traced by gravity over deep time. What matters is not only how large it seems, but how we learn to see it at all. Astronomers use the word void for any region with a galaxy density below the cosmic average. Could this bias how we measure distance? Below average does not mean empty. Gas still flows. Dark matter still bends light. Dwarf galaxies still flicker at the threshold of detection. The distinction is statistical, and statistics are the language of truth when the canvas is the whole sky. Early hints came from radio surveys that listened for the faint whisper of neutral hydrogen. That whisper, tuned to a specific wavelength, marks where gas sits even when starlight is dim. Counts dipped across a broad swath, then dipped again after several careful cuts. Independent teams checked microwave maps that preserve the afterglow of the young universe. A subtle cold patch lined up with the underdensity, inviting both excitement and doubt. Doubt is the discipline that keeps wonder honest. The effect of a shallow region on passing light is small. Photons lose and gain energy as they climb in and out of gravitational wells. If the well is not as deep as usual, the net shift changes by a hair. Over billions of years, a hair can matter. We call that cumulative nudge, the integrated Sachs-Wolf effect, tiny gravity energy kick, meaning evolving structure sculpts the oldest light just a little. One patch on one map is never decisive. Scientists stack evidence like bricks, then test whether the wall stands in a strong wind. They average across many apertures, rotate sky cutouts, and compare to synthetic skies grown inside supercomputers. We align many cutouts on the suspected center, average them, and compare against shuffled controls. The synthetic skies encode only the rules we already trust. If the real sky behaves unusually compared with those, we look again with finer tools. Finer tools begin with better catalogs of galaxies. Counting is an art because telescopes are not equally sensitive across the field. Dust within our own galaxy blocks light in complex patterns. Bright nearby stars create glare that hides faint, distant targets. Selection effects, which are the quiet preferences inside an observing program, can mimic structure where none exists. Redundancy across wavelengths cures many of these illusions. Infrared surveys lift the veil where optical images struggle. Older stars glow best at those longer wavelengths, and dust scatters them less. When wide areas are scanned to great depth, the picture of the suspected valley gains detail. There is a clear gradient in the number of galaxies rather than a sharp cliff. So it is not a hole, it is a wide, gentle underdensity. Gradients are clues that guide us from raw counts to physics, because continuous change is easier to model and to test. All of this sits inside the larger pattern we call the cosmic web. Gravity acting on dark matter builds a lattice of filaments and knots. Gas collects along those scaffolds and cools into stars. Where strands cross, clusters grow fat. Between them, Low-density basins swell as matter drains away. The balance between clustering and emptiness encodes how fast structure grows, which in turn depends on the composition of the universe. Imagination leaps fast when a feature looks extreme. It is tempting to invoke new fields, exotic particles, or unexpected geometry. The sober habit is to test mundane hypotheses first. A deep dip in counts on a flat map could be a stack of several modest basins arranged along our line of sight. Compress depth into a plane, and the stack looks like one crater. Only by sorting galaxies by distance can we tell whether the shape is a single bowl or a layered shelf. Distance at these scales is inferred from redshift, which measures how expansion stretches light. That yardstick is subtle because galaxies also move under the pull of nearby mass. Those random motions add noise. With huge samples, noise averages down. With sparse samples, noise can mislead. Calibrating with standard candles and features in galaxy clustering tightens the scale and reduces the chance of confusion. Every map needs an error model. Groups debate whether the probability of seeing such a wide and lean zone is modest or tiny under standard assumptions. Differences shrink when pipelines are harmonized. Choices about masks, filters, and thresholds can shift a significant score by more than you might expect. Reproducible code and open data let other teams replay the analysis and expose sensitive steps. Headlines prefer certainty, but careful studies embrace measured language. The responsible position keeps two lines in mind at once. First, the region does seem underdense when checked with multiple tracers. Second, its size sits close to the tail of what well-tested models already allow. Learning lives at those tails, where ordinary physics is stretched but not broken. That is where method improves fastest. To see how ordinary physics could carve a broad valley, rewind the cosmic clock. Tiny ripples, seeded by quantum noise, were inflated to astronomical scales. Denser spots pulled in more matter. Leaner spots gave up what little they had. Nonlinear growth amplified the contrast. Voids merged like soap bubbles, leaving irregular chambers whose sizes follow a characteristic distribution that we can simulate. Simulations begin with a box filled with particles that attract one another. The initial ripples match patterns preserved in the ancient microwave light. As the box evolves, filaments emerge, walls form, and cavities open. Analysts then measure the abundance of voids of each size and project the result along lines that emulate a telescope. With large basins appear naturally, with some frequency, our suspicion fades. If they are rare, the choice is not immediate disbelief. It is a prompt to test assumptions in the model and in the observations. At the center of these tests sits the rate at which structure grows. The growth rate depends on how much dark matter clusters and how dark energy, which describes the acceleration of expansion, stretches space. If the acceleration behaves differently from a simple constant, large voids might be slightly more or less common. We do not leap to that claim. We cross-check with weak lensing. Mass distorts background shapes, which traces mass directly by its small effect on galaxy shapes. Weak lensing maps across the suspected region show a shallow dip rather than a dramatic plunge. For a broad underdensity, lensing should show a shallow wide minimum, not a sharp well. because mass is missing gently, not abruptly. That pattern fits the idea of a broad, gentle underdensity. Microwave maps cleaned of local emission reveal a cool spot with a smooth profile. Not a crater, just the kind of slight temperature dip an extended underdensity can cause over long paths. Smoothness again argues for a gradient, rather than a hole with walls. Galaxies are present, just less frequent than elsewhere, at similar depths. Even mild underdensities matter when you fold them into precision work. Time delay measurements used to weigh cosmic expansion can be nudged if light paths cross lean terrain. Supernova counts inside the basin can run low, which skews averages unless corrected. Radio maps that chart neutral hydrogen might undercount features there, changing reconstructions of large-scale flows. None of these shifts are large by themselves. Together, ignored biases accumulate. The cure is craft and crosstalk. Teams publish pipelines with full provenance. Others replay the same sky with small controlled changes. Does the dip survive when the brightest foreground sources are masked more aggressively? Does it persist when the noisiest fraction of the data is removed? Do parallel regions elsewhere behave like proper controls? The culture rewards verification as much as first sighting. Instruments evolve quickly, and each advance brings new risks. Wider fields mean more variation in sensitivity across the detector. Longer integrations expose drifts in calibration. Correlated noise can paint faint bands that masquerade as structure. Mitigation comes from better design and better math. Modern analyses fuse lessons from radio, optical, and microwave work into shared strategies for calibration and validation. Collaboration across surveys unlocks leverage. If a radio map hints at a lean zone, optical teams can dig deeper there. If lensing suggests a mass dip, spectroscopic programs can trace whether the deficit sits at a single distance or is spread across several. With coordination, an odd contour on a map turns into a rich program of measurement rather than a lonely curiosity. Human perception complicates all of this. Our minds are wired to find faces in clouds and meaning in noise. Statistics disciplines those instincts without extinguishing curiosity. When we say unlikely, we must define the family of tests we promised to try before we looked. Post-selection, where a pattern is highlighted because it first caught the eye, inflates significance. Pre-registered tests and blind analyses, where key numbers remain hidden until methods are locked, keep us honest. As the picture sharpens, we translate images into numbers that travel well between teams. The two-point correlation function, pairs by distance, measures how likely galaxy pairs are to sit a given distance apart. The void probability function, chance of empty spheres, asks how often a random sphere contains nothing above a set brightness. Compare these measures inside the suspected basin and outside it. Agreement or mismatch provides clean guidance to theory. Numbers sit on assumptions about the universe as a whole. If one group assumes perfect spatial flatness and another allows a whisper of curvature, their inferences split. If one converts starlight into stellar mass using one population model and another chooses a different template, mass-shaded maps change. Progress comes from labeling assumptions clearly and running sensitivity checks that reveal which choices truly matter. A single feature rarely overturns a framework, no matter how visually dramatic. The remedy for overinterpretation is scale. Build catalogs of many basins, stack them, and compare their profiles. Large samples reduce the chance that one quirky patch dominates attention. With scale, we find whether the strange case is truly off-trend or simply resting in the expected tail. A quiet revolution in inference has helped at every stage. Machine learning tools classify shapes, mend gaps, and flag anomalies. The best versions embed physical priors so the outputs obey conserved quantities and known symmetries. These tools can be wrong in subtle ways if trained on biased examples. Used with care and anchored in physics, they accelerate discovery without replacing understanding. Public releases of survey data have widened participation. Small teams can reanalyze major maps without building new telescopes. Independent checks uncover fragile steps early and convert private doubts into shared fixes. Credit grows through open citations and shared authorship, making verification an honored path rather than a thankless chore. A surprising underdensity turns from a source of argument into a workshop on method. Why does this carefulness matter so much? Because the same maps inform the most important parameters in cosmology. They shape our estimates of expansion, growth, and geometry. A misread valley can nudge those values and seed long debate. Guardrails built now save years of confusion later. Looking forward, deep surveys will chart billions of galaxies with accurate distances. Three-dimensional maps will reveal whether broad basins blend smoothly into expectation or stand as mild outliers. Either outcome teaches. Robust conformity affirms the framework. Persistent difference becomes a new doorway. In both cases, the method grows more precise, and the conversation grows more grounded. Language often betrays us when we talk about emptiness. A hole sounds like a violation of sense. In truth, the spaces between bright knots are structured by the same rules as the knots themselves. They are quieter, not lawless. Paying attention to those quiet stretches completes the portrait of the web, rather than cutting a blank piece from the page. It helps to reflect on the rhythm of progress. A provocative map appears. Careful analysts trim artifacts. New data clarifies the picture. The community settles into a shared understanding. Another puzzle rises at a different scale. Through each turn, instruments sharpen and reasoning matures. Within the suspected basin, galaxy types tell a complementary story. Dwarfs and low surface brightness disks grow slowly where gas is scarce. Star formation histories tilt toward older populations. Gas-rich irregulars still appear along the edges, where filaments feed the interior. These patterns trace the flow of matter as clearly as counts do, and they refine the story from geometry to growth. Gravitational lensing brings another angle. Background galaxies passing behind the region show slightly less shear than typical, a sign of lower integrated mass. The change is small, but it is consistent across several shape catalogs. Shear profiles are broad and smooth, matching the gradient seen in counts. Agreement across weak signals is a persuasive kind of evidence because the systematics differ. Microwave polarization maps add further nuance. Foreground removal is hard, yet several teams converge on a profile that aligns in scale with the dip seen in temperature. Polarization is sensitive to different combinations of effects, so parallel structure there increases confidence. No single data stream shouts the conclusion. When many quiet measurements hum the same note, you do not need a louder instrument. you need to listen. Distance slicing reveals that the basin is extended across several redshift layers, rather than confined to a single thin shell. That geometry fits the stack hypothesis. Several modest basins align by chance along our line of sight, summing to a broad deficit when flattened. Chance alignments are not evidence of new physics. They are a reminder that projection can amplify ordinary features in surprising ways. Even as the case for a gentle interpretation firms up, curiosity does not fade. Researchers explore whether environmental effects in low-density regions lead to specific signatures in galaxy morphology, metallicity, and spin. They check whether gas accretion onto halos proceeds differently, along tenuous filaments. They ask whether faint satellites survive longer when tides are weaker. Each question folds the large picture back into the lives of individual systems. Method continues to improve. Forward modeling, where synthetic skies are pushed through a virtual telescope and reduction pipeline, catches biases that would otherwise remain hidden. Null tests, where analysts check regions that should contain no signal, flag residual systematics, cross-validation between independent teams, finds brittle choices in the code and replaces them with robust ones. The map grows cleaner without becoming over-processed. Communication with the public advances alongside the science, explaining that a void is not truly empty, avoids needless drama, emphasizing that uncertainty is a feature of honest inquiry, builds trust. The real excitement is not in declaring a revolution, but in showing how many careful steps it takes to challenge or confirm a surprising sight. The vocabulary of risk and reward helps keep priorities clear. Chasing every glint would waste precious observing time. Ignoring oddities would leave learning on the table. A measured approach ranks tests by leverage and cost. It backs small, decisive checks first, then moves to deeper campaigns only if signals persist. That structure preserves agility without starving ambition. As data volumes swell, stewardship becomes a scientific task. Teams design archives so that future researchers can trace how every number was made. Metadata carry the context that gives measurements meaning. With strong stewardship, a question asked years from now can be answered with the same rigor as one asked today. Without it, knowledge decays even as storage grows. In quieter moments, many of us return to a simple picture. Imagine watching the web form in time-lapse. Filaments brighten as matter streams along them. Nodes flare where flows converge. Between them, basins deepen as the bright material leaves. The suspected valley is part of that choreography. Seeing it clearly means we are reading the steps more accurately. Not that the dance has changed. The last lesson is the one that threads through all the rest. Hold doubt and curiosity together. Doubt prevents flights of fancy from hijacking the result. Curiosity keeps us open to what the universe is offering. Between those two, progress is steady. In the broad, quiet basin before us, that progress looks like sharper maps, calmer claims, and stronger tests. The road ahead stays practical. We will refine distance estimates, align mass maps with light more precisely, and extend counts to fainter thresholds. We will repeat the analysis on the opposite side of the sky to harvest clean controls. We will fold the results into the larger effort to measure growth and geometry. Step by step, the valley becomes another measured feature rather than a looming mystery. It is easy to be dazzled by crowded clusters and luminous arcs. It takes patience to give the low places equal attention. Yet those low places are where our models are stretched and where our methods are sharpened. The quiet between the lights is not a mistake in the picture. It is part of the picture, and it is where careful seeing becomes a craft. Taken together, that craft will carry us into the next round of questions with steadier hands and clearer eyes. What looked like a hole becomes a lesson in how to know. The valley is not an absence of reality. It is an invitation to read the universe with more care and more grace, even when the light thins. That invitation is open, and we are already walking through it. We can continue from here without losing the thread as we move into fresh measurements that build directly on this foundation. An immediate target is the imprint of sound waves from the early plasma. Those ripples left a preferred spacing in the galaxy distribution that we call the acoustic scale. By measuring that spacing inside and outside the basin, we test whether large features bias our yardsticks. The scale should remain fixed in comoving terms. If the inferred spacing drifts inside the lean region, it signals a hidden systematic rather than a new law. Stability there would quiet one of the louder worries. Kinematic probes add texture to this test. Gas in low-density zones moves with different coherence than gas in crowded filaments. Radio arrays that chart neutral hydrogen in 3 dimensions, using intensity mapping, can watch these flows without resolving each galaxy. The method trades detail for reach. It offers a complementary picture of the valley as a living structure. Where flows bend around the lean core, we see the choreography that statistics imply. Quasars become beacons in the depths. Their light threads long columns of space and picks up fine absorption features from thin gas. That forest of lines traces the density of matter in exquisite relief. If the suspected basin is real and broad, the pattern of absorption should relax across it like a slow breath. Comparing that profile with galaxy counts closes a loop between luminous tracers and the dim medium that fills most of the volume. Environmental fingerprints in galaxies help to seal the story. In thin regions, galaxies tend to spin more freely because tides are weaker. Bars grow slowly. Merger histories look quieter and more protracted. Metallicity, which records the cycle of star birth and death, often runs lower because enrichment proceeds at a calmer pace. These are gentle skews rather than strict rules. They provide another axis of evidence that aligns with geometry and mass. Dust and foregrounds still demand respect. The plane of our own galaxy drapes uneven veils across the sky. Tiny errors in removal can write ghost shapes into maps. Teams now practice cross-correlation with templates built from independent tracers of dust and gas. If the signal rises when a dust template is scaled up, that is a warning. If the signal holds steady under such pushes, confidence grows that we are reading the cosmos and not our own backyard. There is also wisdom in studying anti-examples. Patches of sky that look slightly overdense provide a mirror. Running the same pipeline on those regions should produce symmetric inferences in the opposite direction. If the method finds depth on both sides with the right balance, we know that the machinery respects linearity and does not invent drama only in the sparse places. The language of likelihoods guards against overreach. Analysts report posteriors for key quantities, rather than single numbers. They show how results shift when priors are widened or tightened. They offer corner plots that reveal degeneracies. These habits slow the conversation down, which is a feature. Slower talk leaves room for better questions, and better questions leave less room for confusion. Education within the field moves in parallel with research. Graduate courses now teach hands-on reduction with open sky patches. Students learn to build and break pipelines on purpose. They map how errors propagate and how subtle choices in cleaning touch the final science plots. That literacy spreads through collaborations and raises the floor of every analysis that follows. Public engagement gains nuance as these methods mature. People appreciate being shown how uncertainty narrows rather than being told that certainty suddenly arrived. Visualizations that encode density as sound or touch translate the idea of a valley into human senses. The story becomes a shared investigation rather than a pronouncement from afar. Then, precision cosmology thrives on opposing constraints. Distance ladders built from exploding stars measure expansion directly nearby. Ripples in the ancient afterglow measure the same quantity with a long lever. Large features like the suspected basin must fit gently within both lines of evidence. When all three align within known margins, confidence swells in a quiet, earned way. Careful cataloging of void boundaries opens a new route. The edges of lean regions sometimes host rings of enhanced star formation where inflowing gas compresses. Mapping those rings in ultraviolet light tests whether the basin acts as a slow lens for gas dynamics. The effect is subtle, yet across many edges, the pattern should gather, much like faint constellations appear when eyes relax into the dark. Parallel to observation, theory refines the vocabulary for emptiness. Not all basins are alike. Some are elongated, some are perforated by subfilaments, and some are stitched together by shallow saddles. Shape statistics, built from inertia tensors and skeleton finders, sort this family into types. The suspected basin looks most like a composite of several aligned low spots. That reading squares with the distance slices and relieves pressure on exotic ideas. Time adds yet another layer. Structures evolve as expansion accelerates. Lean zones tend to evacuate more cleanly at late times, which softens contrasts in their interiors while sharpening edges. By comparing nearby slices with more distant ones, we can see hints of this evolution. The differences are not dramatic, yet they trace the same arc as our best models. Agreement in trend matters as much as agreement in amplitude. In technical work, small definitions matter. A void defined by galaxy counts is not identical to a void defined by mass. Bias, the relation between galaxies and the underlying matter field, varies with environment and time. Analysts now present both versions and the mapping between them. Publishing that map prevents two communities from talking past one another while using the same word for slightly different things. The structure around the basin hosts its own science. Filament spines carry streams of dwarf galaxies that peel away into the low region. Tidal alignments twist the spins of small halos as they cross the boundary. These controlled imbalances serve as local laboratories for galaxy growth theories. They also let observers design efficient programs that capture the most telling contrasts with minimal time. Even the sky noise becomes a partner. Random fluctuations in detector readouts and atmosphere teach us robustness. If the signal appears only when conditions are perfect, suspicion grows. If it appears across a spread of backgrounds and still behaves, confidence hardens. Noise is not the enemy. It is the tutor that makes good habits automatic. Looking one step ahead, new facilities will scan the sky with a repeating rhythm. The cadence will let us watch subtle changes in brightness that signal lensing by large structures along the line of sight. Those time domain cues can be folded back into maps of the basin and its edges. Light that flickers under a gravity field becomes a living seismograph for the cosmic web. None of this requires abandoning caution. Claims remain conditional. Evidence is layered. Words are chosen with care. The suspected valley teaches restraint by example. It shows how attention can be intense without being breathless. It shows how patience adds weight to a conclusion without making it heavy-handed. When the dust settles, the likely picture is calm. The region ahead is leaner than average by a gentle margin. The deficit spreads across several distances and aligns by chance in our view. Mass maps, counts, and ancient light all whisper the same tune. The melody does not demand a new instrument. It asks us to listen more carefully to the ones we already know. From that listening grows a durable kind of knowledge. The maps improve. The language clears. The next curious contour will arrive, and we will be ready to test it with the same measured steps. Attention will drift to another corner of the sky, but the habits learned here will travel with us. So the valley becomes a lesson written in faint ink. It reminds us that emptiness is patterned, that method matters as much as marvel, and that depth in understanding grows from many small verifications. With that in mind, we move on with steadier measures, keeping both doubt and curiosity close. We are prepared to carry these habits into the next stretch of observation and to refine them with every new pass. Next, we will test the universe's yardsticks inside and outside the valley: acoustic spacing, quasar forests, and neutral hydrogen intensity mapping to see if distances keep their beat. We pick up at the edge of the valley and step across its faint slope. The question is practical now. Do our distance yardsticks keep steady time inside thinner regions, or do local quirks nudge the beat? We will test the familiar rulers one by one and watch whether the pattern holds. Begin with the acoustic spacing set by ancient sound waves. Long before the first stars, pressure and gravity traded pushes and pulls in the hot plasma. That dance left a preferred separation scale among galaxies that we can measure today. The scale is not a single ridge in a histogram. It is a small swell in the chances that pairs of galaxies sit at a certain distance. Analysts call it the acoustic peak. If the valley biased this ruler, the peak would drift or smear relative to control regions. We do not eyeball it. We model the expected curve and fit the data with the same pipeline inside and outside the valley. The pipeline keeps the masks, weights, and filters fixed to avoid accidental tilts. Then we look at the posterior on the peak position. The test is simple in spirit. If the preferred spacing inside the valley agrees with the outside within well-understood error bars, the ruler holds. If it shifts by more than the stated uncertainty, we search for a hidden systematic before we claim a real effect. There is a practical twist. The acoustic peak lives on large scales where survey footprints and edges can matter. Missing wedges or scanning patterns produce ripples in the measurements. To catch that, we build many mock skies using the same footprint and geometry. The mocks carry the acoustic feature by design, so any bias that appears in them flags a geometric culprit rather than a cosmic one. This is the kind of check that turns a pretty plot into a measurement. Now turn to the forest carved into the light of distant quasars. As quasar light travels toward us, thin gas imprints countless narrow absorption lines. Together, they trace the gentle rise and fall of density along the path. In and around a lean region, the forest should look calmer on average, with fewer deep troughs and slightly wider spacing among the darker patches. None of that is dramatic. It is a shift in distribution, not a new kind of feature. The gain here is that the forest responds to gas rather than galaxies, which diversifies the chorus of probes. We do not chase one sight line. We collect many lines that pass near the valley at different depths. Then we stack their transmission profiles after centering them on the suspected midpoint. Stacking increases the signal to noise of any slow, broad change. To avoid stacking our hope along with the data, we also stack control sets drawn from random positions with the same redshift distribution. If the valley stack departs from the control stack in a stable way across many selections, the hint strengthens. Radio surveys add the third perspective with intensity mapping of neutral hydrogen. Instead of resolving each galaxy, we measure the blended glow within coarse cells. That trades detail for speed and uniform coverage. The method is sensitive to calibration drift and foregrounds, so analysts run a battery of null tests. They split the data by time, by instrument subset, and by sky halves. They difference the splits to kill the real sky and search for residual patterns. Residuals that correlate with the valley outline smell like systematics and must be understood before we touch cosmology. Inside the valley, an honest expectation is modest. Weak lensing should show a shallow, wide minimum because mass is missing gently, not abruptly. The galaxy counts should decline smoothly toward the center and rise along the edges. The quasar forest should relax rather than crash. The acoustic peak should stand where theory puts it. The common theme is gradient. A broad gradient is hard to fake across independent probes if the pipelines are clean. People often ask about a cold patch in the ancient afterglow. Maps of that light, after careful cleaning, do show a slightly cooler region that aligns with the valley. It is not a crater. It is the sort of small temperature dip an extended underdensity can produce as light gains and loses tiny amounts of energy while gravity evolves. The effect has a formal name, the integrated Sachs-Wolf effect, which in plain words means that slowly changing gravity can leave a thin fingerprint on very old light. Because the effect is subtle, we present it with restraint. We fit simplified templates to the temperature profile to measure how broad and deep the dip is. We rotate the template around the sky to estimate how often chance alignments produce something similar. We vary the filter that removes our galaxy's foreground emission to test stability. Only when those moves leave the answer steady do we attach meaning? These hints do not shout, but together they point the same way. Accuracy rises when we pair every claim with an anti-claim test. In the maps, that means choosing regions with mild overdensity and running the same pipeline there. If our method is balanced, we should recover opposite-signed, similar amplitude effects. Symmetry is a friend. If we fail that symmetry test, we revise the pipeline before we add weight to any conclusion. Distance slicing sharpens the picture. If the valley is a chance stack of several modest basins along our line of sight, then each slice by distance should reveal a gentle deficit at a different depth. When we integrate over all slices, the features add into a broad floor. Spectroscopic samples provide precise distances for a cleaner slice, while photometric samples offer reach with larger errors. Using both fills the trade space. Agreement in shape across the two is a confidence builder. To turn pictures into numbers, we lean on standard statistics used across surveys. The two-point correlation function, which is the odds that a pair of galaxies sits a given distance apart, should show the same acoustic bump everywhere. The void probability function, which is the chance that a sphere holds no galaxies above a threshold, should be larger inside the valley at the same radius. By comparing these measures inside and out, we avoid arguments over hand-picked visuals. Numbers travel best when the assumptions are labeled in plain words. Some teams assume the universe is perfectly flat. Others allow a whisper of curvature. Some turn light into stellar mass using one family of stellar models. Others use a different family. We report how the conclusions shift under those choices. Often the shift is small compared with the error bars. When it is not, the difference becomes a clue to refine models rather than a reason to trade claims. Method is a character in this story. Analysts now favor forward modeling, where synthetic skies are built with known truth, then pushed through a virtual telescope and reduction pipeline. The result is treated like real data and analyzed blind to the truth labels. Bias that creeps in is measured directly by comparing the recovered values to the known inputs. This practice catches subtle couplings between cleaning steps and statistical estimators that would otherwise hide inside complex code. Blind analysis also enters at the final combination stage. Key numbers such as scaling amplitudes or offsets are hidden by an unknown shift, while analysts finalize the code. Only when the team freezes all choices do they lift the blind and read the true values. The goal is simple: lock the method before seeing the prize, so that human hope does not guide the last round of tuning. Weak lensing deserves a closer look. In this context, lensing means the small shear of distant galaxy shapes by the gravity of intervening mass. Inside a broad underdensity, the mean shear should tilt toward a gentle minimum across many angular scales. The statistics used to measure that include two-point functions of shape components and direct reconstructions of projected mass. Shape measurements are delicate because atmosphere and optics stretch images in their own ways. Calibration against stars and internal tests using rotated shapes help remove those contaminants. Galaxy populations inside the valley add independent texture. Star formation rates tend to run lower on average in the interior. Metallicities lean low because gas cycles more slowly. Disk galaxies preserve thin structures longer because tides are weaker. These are population shifts, not strict laws. They align with the picture of a place where growth is calm and mergers are rarer. When many quiet measurements hum the same note, you do not need a louder instrument. You need to listen. All along, we ask a controlling question. Are we measuring the universe or our instrument? Splits by time, by detector, and by sky position act as mirrors. If a feature flips sign in a difference map, it belongs to the instrument or the atmosphere. If it remains, it belongs to the sky. We also compare against shuffled control stacks that break any alignment with the valley outline. Alignment that vanishes under shuffling is a warning. Alignment that endures is a signal. Communication matters as much as code. We avoid heavy words when light ones will do. We separate summary from speculation and label both. We provide small glosses next to terms that risk losing non-experts. Weak lensing gets a parenthetical that says mass slightly distorts background galaxies. The integrated Sachs-Wolf effect gets a brief aside that says light gains or loses tiny energy as gravity slowly changes. The vocabulary stays short, and the ideas remain intact. The practical payoff arrives when these checks fold back into broader measurements. Distance ladders rely on a clean picture of how light travels through the web. Growth rate estimates rely on an honest map of how mass clusters. If valleys like this one were to bias rulers, clocks, or counts, the bias would leak into those cornerstone results. Early signs are calm. The rulers keep time. The clocks tick evenly. Counts shift gently, in the way expected from a broad gradient. None of this means the valley is dull. It is a proving ground where many methods meet. By passing tests here, the methods earn trust elsewhere. The act of passing also reveals the seams where improvements matter most. New surveys will reach deeper, measure shapes more sharply, and map gas flows with finer cadence. The same suite of tests will run again with tighter errors. Agreement will either persist with smaller bands, or a small deviation will stand out where noise once hid it. If a deviation survives that stronger scrutiny, the next step is to trace its consequences outward. Would a subtle change in the growth rate reconcile tensions between different measures of expansion? Would a mild tweak in how galaxies occupy halos improve the fit to number counts across environments? Would a refined model for dust remove residual patterns in microwave background maps? Each of these is a controlled question whose answer moves the dial a little rather than swinging it wildly. It helps to close this stretch with a clear statement of where we are. Inside the valley, galaxy counts decline smoothly. Mass maps show a broad, shallow minimum. Quasar forests relax. Acoustic spacing holds steady within errors. The ancient light shows a cool patch consistent with a slow gravitational imprint. Taken together, the picture is coherent and modest. It teaches method, even as it illuminates structure. From here, we can follow the edges. The boundary of the valley is where gas compresses, star formation flickers, and orbits twist. Those edges are also where different probes cross-check one another most tightly. By walking that boundary, we will test whether every tool agrees on the slope and the width. If they agree, we bank the win and move on. If they diverge, we have a new puzzle with crisp, local handles. We continue with those boundary tests in careful sequence, tying each result back to the cleanest controls while keeping the language plain and the steps visible. Before we dive along the edge, it is worth tightening the acoustic ruler with variations that test different sensitivities. The spacing imprint is slightly different across directions parallel and perpendicular to our view, because peculiar motions add elongation along the line of sight. Analysts call that redshift space distortion, and it provides a second measurement of how structure grows. Inside the valley, the distortion signal should ease a little, because flows are calmer. If both the spacing and the distortion behave as expected, we gain two linked confirmations from one analysis. Window functions deserve careful attention. Every survey footprint is a stencil that shapes measured correlations. The stencil imprints its own pattern on the statistics, and that pattern can masquerade as cosmic structure if it is not deconvolved. We estimate the window by firing a large set of synthetic points through the same mask and measuring how often pairs appear at each separation. That estimate then corrects the real measurement in a controlled way. A valley that survives such deconvolution earns credibility. Covariance is the quiet backbone of every conclusion. It is tempting to quote small error bars after fitting a sleek curve. The honest path is to compute how different scales talk to one another, and how masks and noise couple modes. We estimate the covariance either from many mock skies or from analytic recipes tested against those mocks. Inside the valley, where counts run thin, the covariance grows. Accounting for that growth prevents us from overclaiming a clean match or a clean difference. The forest method invites its own checks. Metal lines from heavier elements can overlap with the hydrogen features and confuse the inference. Quasar continua vary in subtle ways that bias the way we normalize spectra. To control for that, we fit the average continuum with flexible yet simple models, then test robustness by perturbing the model within reasonable bounds. We also mask known metal lines and rerun the stacks. A valley that appears only when a specific continuum model is used is not a valley. It is a modeling choice. A valley that persists under many small continuum changes is a real feature of the intergalactic medium. Intensity mapping lives on the razor edge between ambition and humility. The sky is bright at radio wavelengths because of our own galaxy and the terrestrial environment. Foregrounds are smoother in frequency than the cosmic signal, so filters can separate them in principle. In practice, instrument responses leak smooth foregrounds into wavy patterns that mimic the signal. The community fights this with cross-correlation. By correlating intensity maps with independent galaxy catalogs, the common cosmic structure rises, while uncorrelated foregrounds fall away. A valley that appears in the cross but not in the auto tells us to trust the cross and keep working on the auto. All three probes meet at a shared expectation. Inside a broad, gentle underdensity, any signal that depends directly on mass should soften. Signals that depend on luminous tracers should soften with a slight delay, because galaxies respond to their halos over long times. Signals that depend on gas should soften in between. Staggered softening across these families is a fingerprint more distinctive than any single map. Maps of the ancient light reasonably add another independent angle through lensing of that background by intervening mass. In such maps, a broad mass dip translates into a small reduction in the lensing convergence field. The reduction should be smooth and wide, with no sharp boundaries. Analysts test for this by stacking the convergence map at the valley center and comparing against stacks at random positions. We can also stack around the valley's edge to search for a faint ring of enhanced convergence, where mass piles up gently. Agreement between the core dip and the edge ring strengthens the geometric picture. Every measurement benefits from null tests that feel almost boring. Rotate shapes by half a right angle and measure lensing again. The signal should vanish. Flip the time ordering of scans and look for differences. Structure should remain while systematics move. Swap the two halves of the sky and recompute the statistics. The picture should hold. Boredom is a sign of maturity in this context. It means we have run out of cheap ways to fool ourselves. Ages are laboratories in their own right. As material flows along filaments into denser nodes, weak shocks and compressions appear. In ultraviolet light, these show up as rims of enhanced star formation hugging the boundary. In radio light, they appear as slight brightening of neutral gas where streams converge. The pattern should be asymmetric if the valley is a stack of several basins at different depths. Some edges look sharper where multiple layers overlap in projection. Comparing edges across position angles teases out that geometry. There is a clean way to encode edge shape without leaning on metaphors. We compute the tidal tensor of the smoothed mass map, which describes how gravity pulls differently along three principal directions. The signs and relative sizes of its eigenvalues tell us whether a point lives in a knot, a filament, a sheet, or a void. Inside the valley, the tensor should lean toward the void and sheet signatures. Near edges, it should tilt toward sheets and filaments. Matching these signatures to the observed gradients ties language to math. Galaxy dynamics offer another lever arm. In quiet regions, the orbits of satellites around larger galaxies are less harassed by encounters. Thin disks keep their symmetry for longer. Warps relax more slowly. We can test this by measuring the fraction of thin, undisturbed disks as a function of distance from the valley center, matched for stellar mass and redshift. A gentle rise toward the interior would add a living kinematic angle to the static maps. We should also ask about the past. If the valley is extended across several distances, did its interior once host more active star formation that later faded, or has it always been quiet? To probe that, we reconstruct star formation histories from spectral features that respond to populations of different ages. A chronicle that shows consistently older populations toward the center would support a picture of long-term calm. A patchwork of ages would point to a more complex growth path, with intermittent fueling along thin filaments. All of these approaches require a disciplined way to choose controls. A good control region lives at the same latitude relative to our galaxy, has similar exposure time and background level, and sits at a similar distribution of distances. Controls that differ in one of these ways risk importing bias. We therefore build a library of matched controls and rerun the analysis across many members of that library. Robust results move little across the library. Fragile ones drift. A natural concern is confirmation drift, the tendency for teams to inherit one another's pre-processing choices. One group's mask becomes the default for the next, and soon an untested choice hardens into a standard. The treatment is diversity. We encourage independent pipelines built by people who share only the raw data and the abstract target statistics. When such pipelines converge, we believe the result. When they diverge, we learn more from the gap than from any individual curve. Precision invites humility about units and conventions. Distances in cosmology can be defined in several useful ways, and each interacts with the data differently. We keep the narration in simple spoken terms, but under the hood we check that the same story holds in comoving and physical coordinates. We also confirm that the story does not depend on the exact choice of how we convert redshift to distance within the small range relevant for the valley. Stability across these choices builds trust. The interplay between light and mass is a perennial source of insight. Galaxy bias, which ties the distribution of galaxies to the distribution of matter, changes with environment. In lean regions, the brightest galaxies can be more strongly biased relative to the mass than in rich clusters. We therefore avoid relying on a single class of tracers. By mixing bright galaxies, dwarfs, and gas maps, we reduce the chance that a change in bias masquerades as a change in mass. We can even draw on the motions of galaxies to check the valley's presence. Peculiar velocities, the small departures from pure expansion, tend to flow away from low-density regions and toward denser nodes. By comparing observed velocities from distance indicators with the velocities predicted by our mass reconstruction, we can test whether the flow field shows a gentle outward drift from the valley. Agreement in direction and scale adds dynamical weight to the static picture. Some listeners worry that any broad feature can be painted onto the sky by slow instrumental drifts. That anxiety is healthy. We respond by showing that the valley persists across different instruments and platforms that share no hardware. A feature that appears in optical counts, radio intensity maps, and microwave lensing, each built with unrelated detectors and calibrations, is unlikely to be an echo of a single drift. Diversity in hardware becomes a scientific argument. At this point, it is fair to ask what would truly surprise us. A sharp wall would be surprising because it would suggest a process that evacuates matter quickly. A strong, narrow lensing minimum would be surprising for the same reason. A large offset between where mass dips and where light fades would also be surprising, because it would mean galaxies abandon their halos, which they cannot do. The absence of these surprises is not dull. It is the confirmation that slowly evolving gravity explains a great deal of the sky. Let us come back to the acoustic ruler with a more refined test. We can measure the spacing not only as a single number, but also as an ellipse that stretches differently along and across our line of sight. That shape test, known informally as the expansion anisotropy check, asks whether distances scale the same in both directions after we assume a model to convert redshift to distance. Inside the valley, the shape should match the outside if the model is sound, and if the valley is not bending our yardsticks. A match strengthens the claim that rulers keep their beat everywhere. Cross-correlations between probes tighten the web of checks. We can correlate galaxy positions with the lensing map to measure how strongly light traces mass at different depths. We can correlate the quasar forest transmission with galaxy density to ask whether gas relaxes as galaxies do. We can correlate intensity maps with both, building a triangle of relations. If all legs of the triangle lean in the same direction by the expected amount, we trust the geometry of our understanding. Communication remains part of the craft. We keep sentences short when ideas risk piling up. We define terms in place so no one needs a glossary in hand. We speak plainly about uncertainty. We show not only the most flattering version of each plot, but also the versions that test the edges of the method. The aim is not performative caution. It is to earn the listener's confidence by showing the work as clearly as the result. With that ethos, we can say where our knowledge rests today. The valley is real, as an underdensity stretched across several depths. Its effect on light is small, but measurable when many lines of evidence are stacked. Its signature is consistent across maps that respond to mass, to gas, and to stars. The instruments we use disagree in their details, but agree in their verdict. The remaining uncertainty lies in the exact profile of the dip, and in the precise way bias behaves in such calm environments. When we look for tension with other cosmic measurements, we find little to worry about. The valley does not derail our estimates of how fast the universe expands. It does not tilt our measures of how quickly structures grow beyond what our error bars already allowed. It does not demand a new ingredient in the cosmic recipe. It does, however, remind us that broad features can nudge results in subtle ways if we forget to look for them. That reminder has practical consequences. Future surveys are planning their observing strategies now. They can wait their time to ensure that regions near suspected valleys receive the depth needed for clean cross-checks. They can design calibration schemes that revisit standard patches often enough to catch drifts before they settle. They can invest in mock skies that include realistic instrument imperfections along with cosmic structure, so that pipelines are trained on messy truth rather than tidy cartoons. Education rides along with these plans. Students who learn to build covariances, to treat windows with respect, and to favor cross-correlations will carry those habits into the next decade. The best legacy of a careful project is not only a result, but a cohort of people who can reproduce and extend it. The valley gives them a stage on which to practice, fail safely, and then succeed with confidence. If a listener wants the shortest possible summary, it is this: emptiness is structured. Broad underdensities soften many signals by a little. When many small softenings line up across independent probes, the picture becomes persuasive. The valley we have studied shows exactly that pattern. The sky is teaching consistency more than surprise. We can close this section by returning to the human side. Our minds like crisp edges and dramatic turns, yet the universe often writes in gradients. Learning to appreciate those gradients is part of becoming fluent in cosmic reading. It is not lesser wonder. It is a quieter kind that lasts longer because it rests on method and on pattern, not on single striking anomalies. From here, we walk the boundary with purpose. We will compare the slopes inferred from mass, light, and gas. Test whether those slopes cross at the same radius, and confirm that the same picture appears on the opposite side of the sky, where no valley is suspected. With those checks in hand, we can move on with confidence to connect this local structure to the wider web that binds the universe together. We return to the valley, not as a mystery to solve, but as a place to measure with fresh, converging tools. The final goal is simple to say and careful to do. We need a clean, shared profile of the slope and the width, written in numbers that travel across methods. Then we test whether that profile is ordinary within our best framework, or leaning toward the tail where the uncommon lives. Begin with mass traced by weak lensing. We reconstruct the projected mass field from the small, coherent twist of distant galaxy shapes. The result is a smooth map where low values mark lean regions. Inside the valley, that map should show a broad minimum with gentle shoulders rising toward the edges. We can summarize this with a radial profile, an average of mass as a function of distance from the center. The profile's depth and width are the two key numbers to compare with other probes. Next, measure light with galaxy counts, corrected for selection effects. Counts should fall in step with the mass, but with a bias factor that depends on environment and galaxy type. We derive a similar radial profile for light and compare it to the mass profile. Agreement in shape is more important than perfect agreement in amplitude, because bias can stretch or compress the light relative to mass. Where shapes disagree, we learn about how galaxies populate halos in calm terrain. Gas offers the third view. Intensity maps of neutral hydrogen provide a projection of where the diffuse gas sits. Their radial profile should thread between mass and light, because gas responds to both gravity and star formation. If gas lags mass in the center and leads light near the edges, the three profiles will cross in predictable ways. Crossing radii and relative slopes become compact measurements that summarize a lot of sky in a few numbers. Profiles by themselves do not settle the question of ordinariness. We need a playground of mock universes that share our survey's quirks. We grow a large set of synthetic skies, each obeying the same rules of expansion, growth, and composition that our best model encodes. We pass them through virtual telescopes, shaped by the same masks and calibration drifts. Then we measure profiles in the mocks, as we do in the data. Where the data profile lies within that family tells us whether the valley is common, uncommon, or uncomfortably rare, under the rules we trust. There is a human temptation to reach for a single score. Resist it. We report not only a probability, but a map of sensitivities. How does the answer move if we alter the assumed growth rate within current bounds? How does it move if we vary how galaxies trace mass? How does it move if we adjust how gas cools in low-density regions? The valley becomes a set of levers we can push to learn which assumptions matter most for features at this scale. Edge physics then takes the stage. Where the profile turns upward, gas compresses along gentle folds. Star formation rises modestly there. Satellite galaxies swing in and out on elongated paths, twisting their spins by small aligned amounts. We can measure those alignments and check whether they rotate smoothly as we move around the rim. A smooth rotation argues for a single, extended basin. A patchy pattern argues for several overlapping basins along our view. A clean laboratory sits on the opposite side of the sky. We select a control region with no suspected valley and repeat the entire program. Lensing, counts, gas, profiles, and mocks. Parity between the two lines of effort is essential. It catches the invisible bias that creeps in when attention leans too hard on one feature. If both regions lead to similar conclusions about growth and bias, We bank that as method working well. If they differ, we dissect which step carried the difference. We also revisit the ancient light with refined filters. The cold patch aligned with the valley deserves a new pass, where the foreground removal is tuned by cross-validation rather than hand choice. We train the filter on small patches where we know the foreground and then apply it to the region of interest. We quantify how the profile of the temperature dip changes with the filter family. A stable profile across families supports a real imprint. A profile that wanders is assigned to pause before attaching physical meaning. As the measurements converge, we roll them up into a summary that respects their differences. Mass speaks with one kind of noise. Light speaks with another. Gas speaks with a third. We present the profiles on the same axis with uncertainties that reflect those real differences. The single page where they meet is the page to remember. It is the snapshot of what we think we know now. Now a broader question returns. Do valleys like this, when stacked into a census, change our view of the large-scale web? We build a catalog of basins with similar depth and width across the sky. We measure how often they occur and how they cluster with one another. If their abundance and pattern line up with theory, our trust in the model grows. If not, we do not leap to a new ingredient. We first check the scaffolding, selection, masks, and the choices that once fooled us. Linfree. If an honest tension remains, we trace which parameters shift to close the gap. The growth rate could tilt a little. The relation between galaxies and mass in quiet zones could bend. The expansion history could nudge within its current window. None of these shifts rewrite the book. They adjust a line or two on a page. That is how progress usually looks when data and theory already agree well across many other tests. There is poetry in the restraint. A measured adjustment that makes many maps fit at once is more beautiful than a dramatic claim that fits only one. The valley teaches that kind of beauty. It asks for patience with gradients, respect for profiles, and delight in agreements that form quietly from independent directions. We are not alone in this work. New instruments are coming online that will map shapes more sharply, spectra more slowly, but more deeply, and gas more widely. With them, we will trace the web in 3 dimensions with finer fingers. The same valley will be looked at again with fresh eyes. If the profile holds, the idea holds. If it changes in a repeatable way, we will learn something new about how instruments and inference dance together. Communication remains a partner from start to finish. We share code that others can run without special knowledge. We share data with enough context that future analysts can recreate our choices. We write summaries in clear words that carry the logic from raw number to final sentence. When we miss, we correct in public. When we succeed, we thank our critics for the shape of the success. We close with the profile itself, measured in the 3 voices of mass, light, and gas. The valley's depth is gentle, its width is wide, and its edges are smooth. It is not a hole where law fails. It is a place where law is quiet and persistent. Seen this way, the valley is less a surprise than a syllabus. It teaches how to test, how to compare, and how to listen when the universe speaks softly. From here, the next honest curiosity is whether other deeper basins exist that press harder on our models. That path leads to a census across the sky and to sharper instruments built with the lessons learned here. The work continues, not in leaps, but in steady steps that let awe and rigor travel together. To grow a profile that others can reuse, we start by fixing the center transparently. We define the center as the point that minimizes the average mass within a wide circle. Then we test two alternatives: the point that minimizes light and the point that minimizes gas. Each choice produces a slightly different radial curve. If conclusions depend on the exact center, we say so and show the spread. If they do not, we settle on the cleanest definition and carry it forward. Finding the boundary is as important as finding the center. Edges are not walls, they are slopes. We locate them by searching for the radius where the gradient, the rate of change per unit distance, is steepest. We repeat this in angle slices to see whether the edge is round or lopsided. A round edge argues for a single basin. A lopsided edge hints at overlapping layers. This measurement does not care about poetry. It cares about where change is fastest. Different teams prefer different void finders, the algorithms that mark low regions in a three-dimensional map. One kind grows bubbles around empty seeds and merges them when they touch. Another kind carves the map into catchments, like a rainfall diagram, and identifies the basins where flows would collect if the map were upside down. We run more than one method on the same data. Agreement gives confidence. Disagreement gives a starting point for study. Light profiles raise an old question. Galaxies are biased tracers of mass. In thin regions, the brightest galaxies can cluster more or less strongly than the mass, and the relation can change with distance from the center. We model that relation with a simple curve whose parameters float within a reasonable range. Then we ask how much the mass profile needs to move to match the light profile after bias is allowed to breathe. If the required move is small, the two pictures agree in substance, even if they differ in height. Gas adds a helpful pressure gauge. In quiet zones, gas cools slowly and forms fewer stars. That means more gas remains neutral and visible to radio maps, but at a lower density than in busy filaments. The profile should therefore dip, though not as deep as the mass. The exact order matters. If gas dips deeper than mass, we have misunderstood cooling or missed a selection effect. If gas dips much shallower than light, we have misunderstood star formation in calm environments. The order becomes a checklist. The data must pass. Shape measurements carry their own craft. Telescopes blur tiny galaxies into small smudges. Air and optics stretch those smudges along subtle directions. Analysts model the blur using stars in the same image because stars are true points. They build a smooth map of the blur and correct galaxy shapes for it. Any error in this correction leaks false shear into the measurement. We test for that by looking for patterns that should not exist, such as a curl-like signal that gravity does not make. If that curl appears, we refine the model until it fades. Beyond blur, we check how selection interacts with shape. If round galaxies are chosen more often in one part of the sky, the average shape will drift even without lensing. We simulate the selection process on fake images and confirm that the recovered shear is not a ghost of the selection. Only then do we trust the map enough to read the valley's mass directly from it. Uncertainties deserve a home at every step. We publish not only the best-fitting profile, but also the full range of profiles allowed by the noise. We carry those ranges into every cross comparison so that the final overlap between mass, light, and gas is honest. A tidy picture with hidden error bars is a story. A tidy picture with visible error bars is knowledge. When the three voices meet on one page, we compress their agreement into a few stable numbers. Depth at the center, width at half depth, slope at the edge, crossing radii between mass and light, and between gas and light. Each number comes with its uncertainty and with a note about how it was measured. This distillation turns a complex map into a set of handles that other teams can lift and test. With those handles, we step into the family of mock universes. We group the mocks by small changes in their basic rules. In one set, structures grow a little faster. In another, galaxies sit a little differently inside their halos. In a third, gas cools a little more slowly. We measure the same depth, width, slope, and crossings in every set. Then we ask which set resembles the data most closely, and whether that resemblance is meaningful or just chance. A useful way to think about this is as a map of sensitivities. If a small change in the growth rate always makes valleys deeper, and if our valley prefers a slightly deeper profile, then the growth rate becomes a lever that can ease the tension. If a small change in how galaxies occupy halos makes almost no difference to valley width, then that lever is unhelpful here and helpful elsewhere. Sensitivities let us spend attention where it returns the most understanding. Profiles also link to the motion of galaxies through the velocity field. Matter flows away from thin regions and into rich nodes. We test this by measuring the small departures from pure expansion using distance indicators that translate brightness or size into distance. By comparing observed flows with those predicted from our mass map, we check whether motion points outward as it should. Flow that matches in direction and strength is motion that confirms the map. Ages reveal more than depth. If the valley is a stack of several modest dips aligned by chance, the edge will look sharper in the directions where layers overlap and softer where they do not. By cutting the profile into angle wedges and comparing slopes, we can see whether the border behaves like a single ring or like a lumpy necklace. The difference is subtle but visible with careful averaging, and it tells us whether projection plays a leading role. Once the picture is stable, we ask whether the valley matters for other careful measurements. Time delays between multiple images of a background source, used to weigh expansion, depend on the mass along the light paths. A broad dip nudges those paths a little. We estimate the size of that nudge by tracing Mach rays through the mass map and computing how arrival times shift. The answer is small, but small matters when stacking many measurements. We keep a table of such nudges so that other analyses can include them without repeating our work. Calibrations must breathe the same air as the measurements. We collect a set of standard patches on the sky, where many surveys overlap. We return to them often to catch slow drifts in brightness scales, shape measurements, and noise properties. Any study of a broad feature should include a record of how these standards behave during the project. Without that record, a quiet drift can be mistaken for a quiet basin. Communication with peers happens in layers. We write a brief note that offers the distilled numbers and a figure that shows the three profiles together. We write a longer paper that opens every step of the pipeline and points to code that anyone can run. We offer a seminar that walks through the choices and the places where we hesitated. This scaffolding invites critique that arrives early, when it can help, rather than late, when it can only annoy. It is worth saying aloud what would count as a genuine shock. A sharp wall in mass without any corresponding feature in light would be strange. Light and mass are not identical, but they do not divorce. A deep, narrow lensing pit would also be strange in a universe where gravity evolves slowly. Neither appears here. Instead, we see a soft dip, smooth shoulders, and agreement across methods. The surprise, if any, is that normal physics accounts for yet another curious contour. With the valley measured, we look outward to the census of basins across the sky. We build a catalog with uniform rules so that each entry can be compared to the next. We record position, depth, width, edge slope, and the quality of the surrounding web. We record how trustworthy each number is. Then we study how these basins cluster together, whether they avoid one another more than chance, and whether their properties vary with environment. This catalog becomes a backbone for future tests of growth and geometry. The census also lets us test fairness. If our instruments or methods quietly prefer certain parts of the sky, the catalog will show patterns that should not exist. A drift with latitude, a trend with observation time, or a difference between morning and evening scans would all warn us to check our steps. Fairness in the catalog reflects fairness in the raw work that built it. Outreach circles back here too. When we show the valley to people who are meeting the idea for the first time, we choose gentle comparisons. We do not say that the universe has holes. We say that the web has basins where matter is thinner, and that those basins are part of how structures grow. We show how several quiet clues agree, rather than how one loud clue commands. Clarity in outreach reinforces clarity in thought. In the background, better instruments begin to speak. Cameras with finer pixels and steadier shapes reduce the burden on correction. Spectrographs that gather more light reveal fainter galaxies and sharpen distances. Radio arrays that map larger patches with regular cadence lift the fog around gas. The same valley under these new eyes should look the same within smaller error bars if our picture is right. If it does not, the difference will point to exactly which step needs rethinking. There is a final kindness we can give our future selves. We keep a lab notebook for the project in public. It records what we tried, what we kept, and what we dropped, with short reasons in plain words. This record prevents forgotten side paths from being misread as decisions and lets others avoid our blind alleys. It also models the kind of humility that builds trust in a community that learns by touching the same sky with many hands. Standing back, the valley teaches a shape of thought. Look for gradients, not cliffs. Prefer profiles to snapshots. Compare maps that hear mass, light, and gas. Stack evidence. Publish your steps. Invite disagreement early. Ask for the kind of beauty that comes from many instruments playing in tune. When those habits are in place, even a quiet basin becomes a strong lesson. So we leave the valley carefully measured, modestly interpreted, and openly shared. The next curiosity is already on the rim of our attention. Somewhere a deeper basin may wait, or perhaps a gentle rise that complicates a different part of the web. We will bring the same tools, the same patience, and the same calm delight in method to whatever shape appears next.